last talk of today is given by Isar Stubbe from Antwerp, and he talks about principally generating modules from a quantale.
Thank you very much. Thanks for having me giving this talk. Thanks to the courageous people in the audience who attend talks between 4 to 6 and 4 to 7 UK time. The title is very precise. I'm going to talk about a very precise mathematical structure, but the work that I have been doing for a while now can be put under the vague header of the study of sheaves on a non-commutative topology. So let me, by way of introduction, be vague for a couple of minutes. So surely a topology is a well-known thing. In topological space, you can make an abstraction of topological space by studying locales or frames, depending on how you want to call them. So a locale is a complete lattice. It has joins and meets, but it's a complete lattice in which finite meets distribute over arbitrary joins. And the idea is that you have a complete lattice with a multiplication on it, with a unit, top element of the locale. On such a topology, just a normal topology, this is a commutative topology, sheaves have been studied in a variety of ways. For example, contravariant functors satisfying a gluing condition, but also if you're also as L sets, so sets with an L-valued equality relation in the sense of Foreman and Scott and later Morseau. But also, and this is an observation by Walters in the early 80s, sheaves on a locale can be described as enriched categories. Very particular enriched categories, which you are able to define because you have a very particular base for your enrichment. So these sheaves, because Walters, who I think in 81, noticed that they can be described as particular, in fact, symmetric, Cauchy complete, enriched categories, and the base for the enrichment was in fact a universal construction on a given locale. So this is what you can do for sheaves on a topology, on a frame, on a locale. Now what I will mean by a non-commutative topology will be, well, what is called, what has been called by Mulvey, the quantale. Something I will define now in a couple of minutes. So here's a name of Mulvey, I think it's 86. Help me if I'm wrong. That's what I will mean by a non-commutative topology. And up to now I've been working not with sheaves because I'm not able to define symmetry if I pass from commutative to non-commutative, but ordered sheaves on a non-commutative topology, and these I think of them, or I used to think of them as not necessarily symmetric, but still Cauchy complete. Categories, enriched categories over, so if Q will denote quantale, so enriched categories over the split idempotent completion of Q, so a universal construction on Q. So these are things I've been working on and been interested in for a while now. But what will be the point of today's talk? It will be to translate precisely this notion of ordered sheaf on a quantale from categories. So if you categories as a language, so the theory of categories, enriched categories, to modules, right? So the theory of modules. So that's the main thing I want to do. So translate the aim is from So why would I want to do so? Well, because maybe not everyone is familiar with enriched categories, so it's a matter of being compatible with other researchers who are aware of or do work with module theory, modules over quantile. So for compatibility reasons. Another is that there is a nice technical simplification, seems technically nice theory to work with these principally generated modules, as they will be called. And finally, it's not surprising that in sheaf theory you are using a lot of modules, because they have a very important meaning, even just in ordinary sheaf theory on an ordinary topology. And this needs some quotes, I suppose, and I think I will put a name like Mikkelsen, a student of Anders Kok, on this. He wrote a very nice PhD thesis precisely on the theory of ordered sets in a topos, and modules are extremely important because they are the internal sublattices. Right, so that's the aim for today, and I should certainly mention that I'm going to present joint work with Hans Heijmans from Antwerp, the student. And if you're interested, you can look up many details in some preprints that we put on the archive. We have reference number 08297. So that's all for the handwave bit. Now I will be precise. Start by giving preliminaries. Okay. So the whole thing starts off by observing that if you take complete lattices and you take supremum preserving morphisms between them, supremum preserving functions between them, you certainly have a category, but in fact you have a tensor category, symmetric, monoid, and closed, but all I care of is just the monoid structure, tensor structure, and it has a unit, so we have a monoid category. The tensor product is in fact the universal solution to the quote-unquote bilinearity problem, and the unit for the tensor is the two-element chain. Right, so complete lattices and submorphisms form a monoidal category. In a monoidal category, you can work with monoids. These are precisely the quantiles. Monoids can act on other objects. These are precisely the modules. Fixing a monoid, you can look at all its modules, and between these modules you have morphisms. And so you have a category of modules on a fixed quantile. Right, so that's the thing. So let me spell this out. So quantile is in fact, if you want to write it in an elementary way, it's a sublattice, right? You work with the sublattice, but on this sublattice you have a multiplication with a unit, so an associative operation which has unit, which I will write as 1, and the fact that it's a monoid in this category for this tensor product means that the multiplication distributes on both sides on arbitrary joints, so the multiplication is not necessarily commutative, and that's why we think of this as a non-commutative topology. That's a quantile. Q module. I will typically write this as an M. So it's another object of sub, so it's a sublattice, but it comes with an action of Q on M, and I will typically write this also a tensor. So, what it really means is that well, we have an action. I always write Q on the right of M, and you have the usual laws like compatibility with multiplication and unity in Q. Okay, so this is a Q module, and the Q module morphism is, of course, well, I will write, say, a phi is, because we're working in the monoid category of soup lattices, is just a soup morphism between M with its joint and N with its joint, but it's supposed to be equivariant for the action. So it's ring theory, but in soup and not in app, right? It's precisely what you think it is. So fixing my quantale, I can now write mod Q for precisely the category which has all Q modules as objects and Q module morphisms as morphisms. There are fancy ways of doing this. In fact, it's a pre-sheaf category, enriched pre-sheaf category on a one object enriched, super enriched category, and so on. This is not important. The only thing which is important is the consequence, namely that modules on a monoid, the category of modules inherits a lot of very good properties from soup, the base category. So what is one of these good properties that we have in the module category? Well, you have direct sums. So some people call this byproducts. So it's if you have any collection, any family of Q modules, then you can compute their, so it's set indexed, but it's arbitrarily large. You can compute their direct sum, so it's something which is at the same time a product and a co-product. And it's just a new object written direct sum of the MIs, which comes with, well, because it's supposed to be a product, it comes with projections. But because it's a sum, it's supposed to come with injections. Right? And what is the only, how can you characterize direct sums? Well, you can just require that whenever you do a sigma j after a pi k, right? So there's an mk as well, and there's a pi k and sigma k. So whenever you compose a, am I doing it the wrong way? Whenever you have a sigma k and a pi j, you're supposed to come up with Kronecker delta jk. So that's to say, when j equals k, it's supposed to be the identity, and when j is different from k, it's supposed to be the zero morphism. So mapping everything onto the bottom element. That's one condition. And the other condition is, well, if you would go the other way around. So if you would compose just first your pi and then your sigma, but on the same object, so same index, and you join them all up. Right, so you have these arrows. There are actually loops on this object. If you add them all up, if you join them all up, you're supposed to find the identity. So that's a direct sum in this category, and it's precisely as it is in soup. Okay, so that's one good thing. So that's categorical property. But in fact, another good thing that comes with these module morphisms is that you have two sets. So it's not just a category; it's a two category, but a very simple one. So you have two cells. So if I have two modules, so always with a fixed amount, alright, and I have two Q module morphisms, a phi and a psi, then I will say that there is a two cell from phi to psi, and I will write it as an order because there is at most one two cell. The definition will be, of course, that for every m in m, so these are soup lattices, right? That phi m is smaller than psi m. So it's just pointwise order, but it does give your category, but it makes it a two category, a locally ordered two category. Okay, and because it has two cells, because it is a two category, you have adjoints in adjoints. So it's just a two categorical definition of adjoints. What are adjoints? If you have two morphisms in this category, module morphisms, but this time they go in opposite directions, then you will say that phi is left adjoint to psi, if and only if, so this is the definition, if and only if you do phi first and then psi, you are bigger than the identity on M, and if you do psi first and then phi, then you are smaller than the identity on M. Okay. This is a definition. Alright. And one thing which is also clear if you look at these adjoints. So take such an adjunction. You can easily check that phi is an epi if and only if psi is a mono, if and only if this one is not an inequality which saturates to an equality. Right? And there's a similar law for phi being mono and psi being epi. So I will write this in the usual way, this, so for monos and epis. And in this case I will say that N is an adjoint retract of M. Just to have a word. So this is what I refer to as an adjoint retract. And it's precisely direct sums and adjoint retracts which will be the main ingredients for my definition later on. So note that they are purely categorical. They say something about the quantity of multiples, right? These things. Okay, so this is these are preliminaries. Let me quickly give a couple of examples. So as you would guess, the simplest example is the unit for the tensor itself, so the two-element chain. I will often write it as 2, right? So it's a two-element chain, 0, 1. So in which you have a join, in which you have a meet, and in which 1 is the unit for this multiplication given by meet. And if you look at modules on 2, then you just get submatrices, because there's only one possible action, right? Precisely in the same way that you have integers as unit for the tensor in abelian groups, and if you take modules on the integers, you get abelian groups, nothing more. So this is a perfectly general phenomenon. I will call this the classical case. If I compute examples, I call it the classical example, the classical case. So the other example which will be important today is a locale, or a frame. So I repeat that it is a complete lattice in which finite meets are supposed to distribute over arbitrary joins, which makes it a quantile, but a commutative one, or even Cartesian one. So multiplication is commutative. Are there more examples? Yes, you can, for example, build a free quantile on every monoid. You can look at ideals, two-sided ideals, let's say, in the ring. You can look at what is called Lauvier's real numbers, so positive real numbers, form a quantile. This is probably a good example to mention, just to fix ideas. Also, it's a very general principle which I will now apply to this case. If you take any complete lattice, say S in sup, then you can look at the endomorphisms. So the sup morphisms from say, S to S, which have pointwise joins, because it's a closed category, and where you have composition of morphisms as multiplication and the identity as unit for this quantile multiplication. So this is also an example of quantile. And later I might mention quantiles which come from étale groupoids. It's a construction by Resende, a recent construction. And I might also mention quantiles which can be constructed from sides, small sides, which is a construction due to Walters, but also studied by Frey and Skedrov later on, and probably other people as well. Okay, so here's maybe another example. In fact, a particular case of this example, if you take any set, then you can look at relations on the set. So well, let's say subsets of the Cartesian product of X with itself. Relations are subsets, so you can take unions to compute joins, but they can also be composed, and you have a, say, diagonal as unit for this composition, and this also gives you a quantale, a very Cartesian one in some sense. Right, so now these were the preliminaries. Let me now go to the material I want to talk about. Let me first say a word about principality. So, first of all, it's quite obvious that Q itself, so fix a quantile Q, right? Q itself is a Q module. It's just multiplication in Q, which will be the action of Q on Q. Okay, that's fairly straightforward. Now, if I take an idempotent element of Q, an element which equals its own square, then it can be split, not necessarily in Q, but and split it in the category of modules over Q. So what do I mean by this? Well, Q was a Q module. I'll write Q to the power E. It's not this, maybe not the best notation, but what I mean is take all elements of Q which are fixed by E, then this will be a submodule of Q as Q module. So it's a Q module and it's a sub-Q module of Q. We write sigma E. And it's a splitting. So you have pi E. So what are sigma E and pi E? Sigma is just inclusion. And pi E maps, say, a G to E after G, which is clearly a fixed point for E. So this is a very general construction, and I call such a QE, I call it a fixed point module. Just to have a short name. But I always mean fixed point modules for idempotents in Q. Okay, now it's essentially a consequence of, say, enriched Yoneda lemma. So, as a consequence of Yoneda's lemma, if you have an idempotent in Q and you have any other Q module M, you can certainly write, you can use the action of Q on M, so that the tensor is the action that comes with the module M. You can use the action to write an idempotent on M, which is this guy here. So you send M to M acted upon by E. And it's a consequence of Yoneda's lemma that fixed points of this automorphism correspond in a one-one way with Q module morphisms from a fixed point module QE into M. Right? So what is the correspondence? If you have a fixed point of this guy, so then you can map it to this thing. Okay. And if you have a morphism, so the other way around, if you have a morphism from QE to M, and it's called, for example, zeta, then you can compute its value well, E is always a fixed point of E because it's an idempotent, and so you can compute the value of zeta in E. This is this one-one correspondence, but it allows us to talk about elements, so points of a module, elements of a module, in terms of morphisms. And once we are talking in terms of morphisms, we have our ambient category and its structure to express desired properties. Right? So that's the whole trick. So to pass via Yoneda from elements to morphisms, and then to use our ambient category, which is about morphisms, to express desired conditions. And so this leads to the following definition. So in this situation where we have a quantile Q and we have a Q module M, I say that principal or plug? Plug? Oh. Principal element of M, so a fixed a Q module M, principal element of M is simply, say, element of M at an idempotent in Q is precisely such a morphism. So that's a way of talking about elements, but not any morphism. It's supposed to be a left adjunct. So I'm putting a condition on an element of a module by saying something about its uniquely corresponding morphism. And I will typically write zeta star for such a right adjoint should it exist. So I call this a principal element. Right. Now, moreover, second definition. Now I fix, or I give myself a class or a set of idempotents that I'm particularly interested in for some reason or another. So it's a set of idempotents. But I make sure that the unit is in it. So I make sure that 1 is an element of script E. So I fix myself a set of idempotents, and I do this because I want to control the shape of idempotents in the notion that I will next define. So then I will say that M, a module, Q module, is E principally generated. So as in the title of the talk. So it's E principally generated. If what? Well, of course I want to say that the principal elements of the module suffice to generate the whole module. So I have this bunch of arrows. What can I do with arrows? I can compose them. If I have such a principal element, that's to say an adjunction, I could go from M to the fixed point module and back, doing a zeta star and then a zeta. I end up with a loop on M. I can do this with all the principal elements of M. I have a bunch of loops and I can join them up. And I will require that joining them up gives me the identity on M. So if the identity on M can be written as a join of all zeta after zeta stars, where I take all the idempotents in my allowed set, which I set myself as a kind of parameter, and where zetas are all the principal elements at an idempotent of this set script E. So I said that it was all about direct sums and adjoints. The adjoints, I've put them in by definition. Where are the direct sums? Well, one can prove a proposition. I guess I can put it here. Proposition saying the following. In fact, I will state and then try to argue. So M is EPG, so E principally generated, if and only if it is an adjoint retract of a direct sum of fixed point modules. allowing multiple copies of the fixed point modules. So that's where the direct sums come in. So what is the argument for this claim? So the argument for the claim is that to give so let me write, for notational convenience, let me write all principal elements of M, being the set. I will just relabel them to have a good name. So EIs for the idempotents that are in play, zeta i's and zeta star i's for the adjoints, and suppose that it's I do re-indexing of the family just to have an indexing set. To give such a family of adjoints is in fact, this is equivalent to giving, well, to giving what? Well, I have a whole bunch of fixed point modules, I can sum them up. I have a whole bunch of morphisms, and some go out and some go in of these factors. So they definitely determine and are determined by unique arrows, say a Z and a Z star in and out of M. And the point is that to give an adjoint, a family of adjoints, is the same as saying, as giving these two morphisms which are themselves adjoint. Moreover, it's a fact, so if you compute these things, it's a fact that doing first zeta star and then zeta is precisely the join of all the little zeta stars. Okay, so a family of adjoints is the same thing as an adjunction between this direct sum and the module. And this composition equals this join, so to say that these guys join up to be the identity is to say that zeta star zeta is the identity, and it's precisely what I define to be an adjoint retract. Okay, so that's where the direct sum comes in. Now, these are definitions. Let me compute the classical case. Just to illustrate this notion. Let's see the classical example. So my Q is 2. I take the 2-element chain. So first of all, well, so this guy obviously has two idempotents, but to compute principal elements at 0, well, there is only one, is the 0 element, so I'm going a bit too fast. So in this case, the modules I'm looking at are just sublattices, as I said. So I take an M, which is just a sublattice, and the principal elements of a sublattice at 0, the only one is the bottom element of the sublattice, and the bottom element is always principal at 0. So it's the non-interest. It's a trivial case. It's the non-interesting principal element, right? So I only need to do something interesting. I need to compute principal elements at 1. That's the idea. So let's compute this. So if to say that M in M is a principal element at 1, is to say by my definition that something has a right adjoint qua module morphism, right? So in this case, qua submorphism. So in fact, it's saying that, well, the fixed point module for this idempotent is the whole of 2, and it's saying that that a unique module morphism which corresponds via later with this element. So this was it was a zeta, and it was defined to be tensor with M. Has a right adjoint. It was written as, so this is zeta, Z, it should be an adjunction qua module morphism, so in soup. Okay, because this guy always preserves joins. It's part of the definition of an action. So it always has a right adjoint, but qua order preserving morphism, but not necessarily qua soup preserving morphism. So it has a soup right adjoint, so right adjoint in the category of soup lattices, if and only if this guy, the right adjoint qua order morphism, preserves soups. And you can always compute the zeta star in qua order preserving morphism. So you will see that it's the map which maps an x in M to either 0 or 1. So it's 0 when M, my original principal element, is not smaller than x, and it's 1 if it is. So this is the zeta star. It's always an order preserving morphism, but it should be a soup preserving morphism. So it preserves prima. Okay. So what does that mean? And this is a familiar notion, I have to say, a lattice theory, or a more or less familiar notion. So what this says is that, well, let's write it down. So for every family of, say, ni's, you need to have that zeta star of the join of the ni's is 1 if and only if the join of the i's to the zeta star of the ni's is 1. But this is the case if and only if M is smaller than this join. And this is the case if and only if there exists a J such that M is smaller than Mj. Right? And this is known as total compacity or supercompacity. I don't know. Right? So it's known, or at least more or less known in lattice theory, as totally compact, total capacity, or supercapacity. Okay, so that's a classical case. This is what such a principal element is supposed to be, what it is, and so how you can start to think of it in the more general case as well. With an eye on the clock, I should speed up, and let me just say that let me just compute in this classical example what it means for a soup lattice to be E principally generated. So now the proposition comes in handy. So E principally generated meant, so here E will be the collection of all my idempotents, but only one is interesting. So it means that M is an adjoint retract. So an adjoint retraction R and S of an adjoint retract of a direct sum of fixed point modules. Now in this case the fixed point modules are very simple. You're either a fixed point of 0, in which case you're 0, or you're a fixed point of 1, in which case you're the whole thing. Now of course the fixed point modules of 0 are not interesting. They will contribute nothing to a direct sum. So in fact this is saying that this direct sum of fixed point modules is a direct sum of copies of 2. Right? It's a direct sum of copies of 2. But the direct sum of copies of 2 is a power set, where the set is the indexing set for the number of copies. Right? So this is really saying that you are a power set of a set X. Now, it's easy to compute that when you have a power set of a set, then its principal elements, well look just at this notion of total capacity, the principal elements are the singletons, precisely the singletons. You have this adjunction, making sure that your principal elements here get transposed by R to principal elements in M. You have this vague idea, I'm sure, that well, every subset of a set is the union of its singletons. That's the idea behind being principally generated. And because this guy is the union of its singletons, this explains the condition of principally generated. You can make it explicit. You can say that is the case. So any adjoint retract of a power set is in fact a downset completion of an ordered set. That's the whole point. So with a bit of work, but it's sort of suggested by the situation, you can see that in fact M is the lattice of downsets of the ordered set A, where you can take as elements of A precisely all principal elements of M. So here is a bit of work, but if you're a bit used to this kind of lattice theory, then it's intuitively clear, I guess.
Sorry, what's the downset?
So when you have an ordered set, you can look at subsets, but you want those such that for every element it contains, it also contains all the smaller elements. So down close to subset.
Is it equivalent to say that every element is equal to the sum of all the supercompact elements below it?
Yes. That's precisely what it's saying. That's what the isomorphism is doing. So from left to right, you do as you say, and from right to left, you take joints.
So it's like a very algebraic lattice.
Yes. It's super algebraic. Or totally algebraic. That's what it's called. Okay. So this is the classical example. I didn't say a lot about morphisms, but so the important elements, the principal elements, correspond with left adjoint morphisms. So let's do the following thing. Let's take these modules. I'm still in my classical example, but I'm taking the EPG ones. And I now take, it's a two category, right? I now take only left adjoint module morphisms, so submorphisms between them. So what will happen? Well, these left adjoints will only see the left adjoint elements, or the principal elements of the sublattices. What you can therefore prove is that this guy is precisely equivalent to the category of ordered sets. That's to say, we've already seen that EPG sublattice is a downset completion of an ordered set, while left adjoints between EPG sublattices are completely defined or determined by their restriction to the principal elements, which is just an order-preserving map. And this is what I'm saying here. Right? So let me be a little bit precise. So if you have a guy like this, and if you have another one, you can be interested in submorphisms, which are left adjoint. What I'm saying is that the left adjoint ones are completely determined by their restriction to the ordered set of the principal elements. And this explains this. It turns out to be an equivalence of categories. Another way which might be appealing to explain this fact is, well, you have ordered sets, and you have sublattices. There's a forgetful functor from sublattices to ordered sets, which has a left adjoint, which is precisely the downset construction, suitably extended, so we call it an F. But sublattices, as I said, are modules on 2. The remarkable thing, or one remarkable thing of this adjunction is that both involved functors are injective and faithful, are embeddings. And so you can compute the replete image of the left adjoint, and that's precisely this guy. So this one is equal to map mod. So that's another way of explaining this this business. Right, but it's not necessarily the classical example which is interesting, of course. The idea is that it extends to Well, to begin with the localic case, the localic example, I let my quantale be locale. Then, in a similar fashion, these left adjoints between the E, P, G modules, and I take for E all idempotents once more, on L, is the same thing as the ordered objects in the topos of sheaves on L. Okay, and then the general example. For any quantile, you can compute this thing. So the left-hand side, I've defined it completely. Well, we don't know what sheaves on a quantile are. It's not a defined notion, or at least not yet. But, well, let it be a definition. Let the ordered sheaves on the quantile be precisely this category. Right, so that's the idea. And does it make sense? Well, yes, because it's equivalent to precisely these Cauchy complete categories enriched in the split idempotent completion of Q. So let me write this as Q split idempotent. So it's a confirmation of a previous definition or attempt, let's say.
Is it the split idempotent completion of Q or the Cauchy completion of Q?
Split idempotent.
Okay.
And it corresponds to the fact, so I'm splitting all idempotents corresponding to the idea that I let script E be all the idempotents. But I could take a smaller class for E if I'm only interested in certain idempotents, and then this is just splitting those particular idempotents.
But is that also the Cauchy completion in the sense of enriched category?
No, because then you would have to add direct sums.
Alright.
Those are, as you can see from the formula somewhere, they are defined as a diagram with morphisms satisfying equations which are preserved by...
It's like an reading group.
Exactly, exactly. Okay, so I wanted to say something about symmetry. So I said in the beginning that sheaves on a locale are symmetric Cauchy complete categories. I've thrown away the symmetry because I'm not able to express symmetry if my base is a quantile, not necessarily commutative thing. And I want to do something anyway with the notion of symmetry. So that's what I want to quickly tell you about next. And again, I will use this classical example to force your intuition in a certain direction. So, to say something about symmetry. So like I said, for a general quantile, I'm not able to say something about symmetry of modules on the quantile or categories enriched in the quantile. It's a sort of micro-macro effect or a kaleidoscopic effect that if you want to do something with enriched stuff or with modules, then you need to put in enough material in your base structure. And so to work with symmetric enriched categories, you need to have an involutive quantile, and it will be similar here for my modules when I want to talk about symmetry. So let me first say that involution, which I would typically write with a knot on a quantile Q, is what? Well, it's an isomorphism of sublattices, which is also a morphism of, so it's a morphism of monoids, but which reverses the multiplication. And in fact, it's enough to say, so it's a map, it's a function. So from Q to Q, such that it's enough to say that it preserves order. It's enough to say that it preserves order. It should reverse multiplication. Right, and what else? And it should be involutive, of course. Okay. So this is what I will consider to be, well, this is an involutive quantile, but I consider it to be symmetric. I mean, this is symmetric for me. And of course, symmetric quantiles, where the multiplication is really commutative, falls under this definition by taking the identity involution. Right, so that's an example, the obvious example. As examples, let me say that. So 1Q is involutive evolution if and only if Q is commutative. And another example to show that there are non-trivial examples, if we go back to the relations, then it's involutive because you can switch relations, right? You can switch the argument of a relation. So here, say x, y is in the involute of a relation if and only if y, x is in the relation. Provides an involution. Okay. This can be generalized to endomorphisms on an ortholattice, if you want. Right, so now I want to express, in fact I want to express the symmetry of the principal elements of a module on an involutive quantile. So from now on, my quantile is involutive. And I'm going to say the following. I'm going to define, I'm going to say that M is E principally symmetric. I forgot to say, from now on, I will define E to be symmetric idempotents. So, from now on, I define my favorite idempotents to be the symmetric ones. And I say that M is E principally symmetric. If what? Well, I want to express symmetry of principal elements. So I have one here, and let's say I have another one here. It says that script E is defined to be all the idempotents in Q which are symmetric, so which equal their involute. So E square equals E involute. So suppose I have two principal elements, my E and my F are symmetric idempotents. How can I express that this situation is somehow symmetric? What is the symmetry that I will require from this situation? Well, what can I do? I could compose a zeta with an eta star, and I can compute its value in E, which is definitely a fixed point for E. I could also go the other way around and compute zeta star in eta of F. F is a fixed point of the idempotent F, trivial. And the requirement I'm going to put on this, and well, experience shows that it makes sense, is that the left-hand side is equal to the involute of the right hand. So eta star of zeta of E equals the involute of zeta star eta F. That's a symmetry condition I'm going to require. Again, it's stated in terms of morphisms. So let me try to convince you that it's a sensible thing to do with my, here it is, with my classical example. So let me, for the obvious reasons, take two principal elements at 1 in the classical example. I take two principal elements at 1 because if I do it at 0, I'm going to end up with a trivial condition, always true. So I take M and N principal elements at 1 and 2. So what is the requirement? The requirement for symmetry is that well, my zeta star and my eta star, so this guy corresponds with the zeta. and this guy corresponds to eta. The condition, the symmetry, so is going to say that eta star of zeta of 1 is zeta star of eta of 1. But it really says, so zeta of 1 is m tensor 1, which is m, right? So it's eta star of m is zeta star. Similarly, eta of 1 is n. It's n tensor 1, which is n. And eta star is precisely, well, mapping things on 0 or 1 according to this clause. So what is really saying that n is smaller than m if and only if m is smaller than n. So it's precisely expressing the symmetry of the order on the principal elements. So you have a complete lattice. In this complete lattice you have the supercompacts. E principal symmetry is precisely expressing that supercompacts are not ordered or are flatly ordered. Form a set, not an ordered set. So what is this saying? What does this imply? Well, to be E principally generated and E principally symmetric is saying that you are the downsets of a set. That's to say, the power set of a set. So I'm writing down a very categorical way of describing power sets, right? And power sets are a way to talk about sets if you only speak lattice theory, right? So it's a way of dealing with sets via lattices and more generally of sheaves via modules. Okay, so let me put some conclusions and then maybe a quick remark. So what can we write down as examples? So the classical example, I sort of said it, can be modified a little bit. So if you add the E principal symmetry, then you're adding symmetry of the order. So you're not having ordered sets, but you're having sets. So set as, well, as sheaves on 2, if you want. Localic case. If you do these, if you take these maps of modules which are EPG and EPS on a locale, you get sheaves on the locale. So always E is symmetric idempotents. And so it's tempting again in the general case. It's tempting to define sheaves on an involutive quantale as precisely this map of mod EPG EPS Q. So it's tempting, but is it a good idea? Are there applications, quote unquote? Well, I told you about a quantale that you can build from a site, Walter-style construction. If you plug in the quantale that you can build from a site in this thing, you get the category equivalent to the sheaves on that site. I told you about the quantale that Pedro Rezende and students of his have constructed from étale groupoids. Essentially what they do is they take, so an étale groupoid is a internal groupoid in the category of locales, such that every structural morphism is a local homeomorphism. So what he does is he takes the locale of morphisms of your groupoid and he uses the groupoid multiplication to put a multiplication on the locale of morphisms, and so he invents a very particular quantale from the groupoid, and we can prove that the continuous actions of the groupoid correspond with these sheaves on that quantale that Rezende constructed. I must say that the stuff about the sites and the groupoids is not yet written down, so consider it an announcement rather than a fully proved theorem. But we will put it on the archive it's ready. I wanted to say just one more word very quickly about, because I mentioned it in the abstract, so one more word about what we call Hilbert structure. I'm not very happy with the name, but anyway, so let me just mention this, and so here's a theorem. I will just state it as a theorem and leave it to your imagination to fill in the details. So I'm in the previous case. I have a quantale, an involutive quantale. I write script E for the collection of symmetric idempotents. I take a module on the quantale, then I can prove that it's E principally generated and E principally symmetric, so it's a sheaf if you want, or a sheaf in disguise. If and only if the application, the map that I will now write down, so the map from M cross M to Q, so think of inner products, right? Inner products on a module. Application that I write as follows. The map that I write as follows. I take M and N, two variables, two elements of the module. What can I do with these two elements? And of course I want to make a link with these E principal elements. So recall I have this principal elements like this. I have my M and my N. What can I do? I can push them through zeta star. Between zeta star of M, the zeta star of N. Now I'm in a quantale, a subquantale of my original one. I will compute this. So I will take the involute of the one on the right hand side and then multiply them in Q. Right? So this is an element of Q. So in fact in QE, but therefore also in Q. But I can do this for every symmetric idempotent and for every principal element, zeta. I have a whole bunch of elements in Q and I can join them up. Okay? So it's as if I project my elements in M onto these factors and then compute these quantities and join the whole thing up. Well, M is E principally generated and E principally symmetric if and only if this thing is an inner product. Inner product in the sense that if you fix a variable, you have a module map and that it's symmetric. So this is in fact a notion due to Jan Paseka. He described this in a paper in 1999. Is an inner product admitting a very special set. I'm going to invent or write gamma for the set of all principal elements, let's say. So put it in up to Yoneda again. Admitting this as what has been called basis, not by me but by Resende and Rodriguez. In a paper on the archive last year, I think. So what does basis mean here? Basis means that every element of your module can be obtained as a join of, well, you project your element on a basis vector and then multiply the basis vector by this distance or angle if you want. So this is what this basis thing means. And this is an equivalence. So to be EPG and EPS is equivalent to admitting an inner product which has a basis. And it's this inner product and this basis which we call Hilbert structure. Because this was used by these people, by Paseka and by Resende and Rodriguez. Moreover, for particular quantiles, in fact for the ones which are also local, so the underlying complete lattice is also local, and moreover, as a quantale, so as involutive quantale, it's modular in the sense of right, so two strong conditions. But under these conditions, this inner product is the only possible inner product. Examples of such very particular quantales, precisely the quantales that come from groupoids and from sites. So it's very particular, I agree, but it does have some applications in sheaf theory. And well, I think that's everything I wanted to say. Thank you.
Questions, comments?
If you take the quantile of relations on a set, what do you get for these E-Bridge degenerated symmetric?
I don't know. So I take a module on that quantile and I want to compute the...
What was the E-Bridge degenerated symmetric ones?
I don't know.
No.
You have an idea?
I can guess, but
You have a guess?
I wouldn't like to say without particularly not data.
Isn't that going to be Morita equivalent to the two?
To the set. To what?
Yeah.
So sheaves on a site are just localizations of pre-sheaf categories. Have you given any thought to what the notions of sheaf on quantile, or any kind of characterization there?
No.
Then we go and drink and eat.